And again, like in padding also, if you don't want to lose information or we want to equip more information, we will just pad around the input image so that the information is not lost, because while doing convolution operation we may lose to compress the image. But if you don't want to compress the image, if you need the original size, we apply something called as padding. So again, in this full operation also we are actually increasing the image. So we are something like instead of using dimensional reduction, we are increasing dimensions, or it's not like dimensions only, we are just increasing the scope, like whatever the domain is there, domain is for the input image, that dimension we are increasing. Or we can say we are stretching the image and we are macroscopically going deep into the image so that all the features are equipped. So again, both will have its own usefulness. Yeah, so now we will deep into convolution layer. So what is convolution layer, that we will see. For example, for like typical or standard problems, we will be given input, we will be applying kernels, that is nothing but weights. If you want to think in terms of simple neural network or artificial neural networks, so here also learning parameters are nothing but the weights or of the kernel. So whatever the weights are inside there, we need to optimize that, we need to find the right balance of the weights so that our neural network will be trained properly and it will be able to predict on new data or test data also. So again, gradient descent, all those happens, but in a different way, that's it. So all these neural networks are somehow related to each other. We will pass input, we have to train it, we need to optimize the weights or the learning parameters. We can use hyperparameter tuning. At last, whenever the model is ready, we can just use the predictor or inference, so that on the new test data it will be able to classify, or in a regression case it will predict, or whatever it is, supervised or unsupervised, whatsoever problem, it needs to give some output. So, and that's the main purpose we are doing in reinforcement learning also, and also in like self-driving cars, so wherever, like AI also. So we need to get some output out of it. So, and again, some cases we just find not only the output as inference but some meaningful results also. So yeah, for here we are, if you do classification, we need some output or probability of which class it belongs to. So for example, we have input images, we are taking 3, for example RGB channels you can assume, and the labels you have to keenly observe. We are giving x11, x12, x13, here also x11, but 2 means second channel, 3 means third channel. You can assume as layers also in a simple neural network, what you in artificial neural network also you can relate to like that. So here kernels filter, naming also you can see, and depth is 3 because we are taking 3 image channels, so we are just matched that kernels depth also with that. And here you need to see, if we have 2 kernels, we will and 2 biases, we will get output of 2 by 2, and 2 outputs we will get, because how it performs is nothing but, if we will see y11 dash is the combination of all this, it's nothing by this k11 is mapped over this image, and this this k1, this one is mapped over this, and this one is mapped over this. So for this kernels and for these inputs, we will get one of the like box matrix as an output, and for other filter we will perform the same and we will get another box as an output. So what we are trying to do is, here we need to take this filter, a k11 filter, and we will map that with this over here like this, and this one over here, and this one over here. Then whatever the result we get, we'll sum them and we will add the bias component, this one, and that will be the result over here. Now y121, if you want to see what happens is, we will again take this filter and we will just move one step ahead, and this filter we will step one step ahead, and this filter we will one step ahead, and add this bias, this one. This other bias is for these kernels, right? So this is how you need to match which dimensions. So basically in neural network you need to follow simple basics, is how the dimensions are there, which maps to which, and why using same depth. Like if we have input 3 depths, so we are using kernel also 3 depth, and bias 2 only because kernels are 2, and what dimensional we will get output. So here it's nothing but 2 by 2 into 2, right? Because 2 output matrix vectors, and each of them are 2 by 2. So first, how many of them are there? 2 are there, and then each of them is 2 by 2, or you can 2 by 2, and how many are there? 2. So this again depends on how you classify those, how you want to give a notation for those. And again, if you want to like move, so it will come over here, and this one will come over here, this one will come over here, add them, add the bias this one, and here this with this one respectively, and add this one again will start from here, this one will start from here, this one will start from here, and add this bias. So it goes on. At last this one here, this one over here, and this one over here. We are doing valid operation only, valid cross correlation for suppose, or convolution, because they are just slightly different, like 180 degrees rotation. So here and there we can use the same wording, naming convention also, no problem. And then we'll add this bias. At first we had add this for these things, now this one for this, and we will get the output over here. At first here and here, so all these boxes will be filled. So for this kernels, with this input image, at first we will get over here, and at last we'll get over here. And with this kernel filters, with this input image, at first we'll get over here, and then or at last we'll get over here. So all this will be filled as shown now, using the biases. First one for this kernel, last for this kernels, first one for this kernel, at last this for this kernel. So I think you can map, and so this one for this kernels, first and last for these kernels with the input and biases. Now if I want to show in a broader sense, you can just take this picture into account. So this matrix is represented as a single variable or in a box. So x1, x2, x3, and this k1, k12. So one here indicates the first kernel, and here it is second kernel. In that first filter, second kernel is only filter, but you can assume like first one, second one, third one, because we have 3 input images to match. So these dimensions, again, as I've said, each of them is 2 by 2, and how many of them are there? 2 are there, so 2 into 2 into 2. Let's map with the output thing. And again, they're each of 3, so 2 into 2 into 3 actually. So it's 4 dimensional, because each of them are in 3 in size, because depth is 3. So this one is nothing but we have 3 of them, and each of is 3 by 3. And so these kernels are there. So k11, k12, k13, k21, k22, k23, and bias 1, bias 2 as this one, and output we have y1 by 2. So that's also again mapped over here. So if you want to just roughly see y1, how we are getting y1 is nothing but x1 matrix is multiplied by k1, and that plus x2 is, it's not multiplied, it's convoluted or cross correlation with k12, obviously multiplied element wise, but matrix terms we will just use cross correlation or convolution. We will just use those here and there, those words in a mixing manner. So x3 with k13, because we are talking about y1. If you talk y2, you will use k21, k22, k23, and till depth d. If you want to generalize, x1 convoluted kd1, yeah, you can just see till bias at depth d. Because number of biases is equal to number of output layers units, because here number of biases are 2, number of units output layers are all 2, because kernels also are 2. So yeah, I think you got that. So in forward propagation, basically if you want to generalize, nothing but yi, this thing yi is equal to bi b1. If you just see the first one, so you can get actually idea. From j is equal to 1 to we will go till 3, like means kernel depth, till depth we will go, because nothing but d is nothing but depth, right? This j is nothing but depth, I is 1 to d, and j is till n is nothing but dimensions or number of each filter for each input matrix, dimensions of each filter for input matrix. So how many filters we have? We have 2 filters, right? 2 filters, and each of them we have 3 of them, because that is nothing but dimension of input. So here d is depth and n is nothing but dimension. So here it will be 3, and d will be also 3, because we have 3 input image as a dimension, and depth also 3, right? Actually depth is nothing but this one only, this 3 are there, but here what we are saying is dimensions 3. So 3 input images, 3 channels, so we will use the depth of kernels also 3, so that we are talking about dimensions over here. And d is nothing but number of filters actually. So k1, k2, k3 means third filter kernels, so that it that is nothing but d here over here. So here and there the naming changes. So depth also will call that, we can also call this as depth, but here we are, in this particular thing what we are calling is this has dimensions n and this has dimension d.